Welcome to the Julia for Data Science video course by Pact Publishing. My name is Alvo Balbaret, and I teach programming courses. I have a background in physics, but have worked in the software industry for a large part of my career. I am the author of the first book published on Julia, and I am currently working on a book called Deep Learning with Julia. In this introductory video, we will give an overview of what you can expect in this course. The series will teach you how to work on data science projects with Julia programming language. Why Julia? Because it is a fast, high-level, free, open source, and very readable language, with a steadily growing community. And you won't need C code anymore to get the performance you want. We start with a thorough introduction to Julia itself. Then, we go on to work in DataFrames, with data from various data sources. We see how to perform common statistical data explorations and how to visualize these. We end the series by showing some machine learning techniques in action. The goal of this course is to add Julia to your data science tool belt, so that you can start applying it in real data science projects. And perhaps you will pick up some new data science topics along the way. We'll proceed in a very practical way, showing and explaining the code and its resulting output. And you are highly encouraged to try these things out for yourself, on the examples given and on your own data sets. Throughout the course, we'll use and develop the techniques on the well-known Iris dataset, so that everything is familiar and easy to follow. Don't worry, you don't need to know Julia to start this course. We explain and try out everything you need to know. Here, you see some typical code screens and plots developed in this course. To sum things up, after working through this video series, you will be able to apply Julia in data science applications and other software projects, and rediscover the joy of writing elegant and fast code. So, let's begin this journey together, and I hope to see you there. Hi, and welcome to this video course entitled Julia for Data Science. In this section, we will get comfortable with the Julia environment and explore the most common data and control structures. We'll also learn how to write functions and how to work with matrices. Now we move on to the next video in this section, in which we install Julia and take a look at some common development environments. At the end of this video, you will have a good foundation for working with Julia and running a Julia platform. In this video, we're going to take a look at how to build up your Julia working environment by installing Julia and showing the most common development choices. So, let's begin. First, we need to install the Julia binaries of the stable current release. To find and download the installer specific to your Windows, OS X, or Linux platform, type the following link into your URL, julialang.org/downloads. Open the installer and the archive manager specific to your system, and it will install Julia in a location of your choice. To verify the installation, open a terminal on your system. Type Julia and enter. After a few seconds, the Julia shell or REPL environment, short for Read Evaluate Print Loop, will start up. It prompts you to enter Julia code. For example, println, brackets, quotes, I love crunching data, quotes, close brackets, and enter. You can test out the pieces of code in the REPL. For example, check out the screen on the left. When satisfied, you can copy the code to a Julia source code file by selecting it, pressing enter, and pasting it into a file. Let's name that file 1_2.jl. All source files have the extension .jl. See the screen on the left. You can also execute that code from a command line by typing julia 1_2.jl and enter. You can start Julia with a lot of options. Type Julia -H for a list. Here is some useful information. In the REPL, you can clear the screen by pressing Ctrl and L. Previous commands, even between REPL sessions, can be retrieved with the up and down arrow keys. Typing a question mark and the name of a function, for example mean, prints out help information about that function. Additional Julia functionality can be added by installing packages, often called libraries in other languages. Exit from REPL with Ctrl-D. If you like to work in a programmer's text editor with plugins that support Julia development, then Sublime Text is an excellent choice. Follow the steps on the screen to install it. From the menu, choose Tools, Syntax, and then Julia to start Sublime Text in Julia mode. Now we have syntax highlighting, auto-completion, and code snippets. For example, type if and enter to get a template for the if statement. Ctrl and B executes a Julia script and shows the result or possible errors. If you prefer a more interactive notebook environment, like many data scientists, use Jupyter. This enables you to execute a code line or a few lines of code at a time, and immediately see the results embedded. You can also add your own comments, effectively turning it into a document with code, explaining text and graphics. You can follow the instructions on the screen for installation. For the Jupyter Notebook, we need the iJulia package. Add it to your environment by giving the following command in the REPL: pkg.add, open bracket, quotes, iJulia quotes, close bracket. After installing, you can start a Julia notebook from within REPL with using iJulia notebook, or from a terminal with Jupyter Notebook. If you don't want to install Julia on your computer, or you don't have a desktop at hand, you can work with Julia in the cloud through Julia Box. juliabox.org. This web service starts up a private Julia instance for you. You can work with the built-in Jupyter Notebook just as you would with a notebook on your own computer. And you can upload and synchronize files with your Google Drive. We do have a lot of options here, don't we? In this video, we have built ourselves a solid Julia working platform and gained a first impression of what Julia code looks like. In the next video, we will explore the basic building blocks Julia uses for storing data in applications. Hi, in the previous video, we learned how to create our Julia environment. In this video, we are going to take a look at simple data like numbers, strings, and arrays, and how to use them in Julia code. Here, we just opened our REPL. The core of our business is data. We store data in variables, and data values come in different types, such as the following examples. Julia has a dynamic type system, which means that types can be omitted in code. When you use a variable that is not defined, like flowers here, or mistype the name of a variable, we get an undef var error. Julia does not know a variable with the given name. To compare two values and see if they are equal, we use double equals sign. Note we do not have to indicate the type in code. Julia infers the type from the value. But internally, Julia gets track of the type of variables, which we can see with the type of function. Julia is strongly typed. It forbids operations, so-called methods, that are not defined, like plus on a string and an integer. Notice how Julia specifically searches for a plus method with the types of the variable flower, which is ASCII string, and the literal 28, which is int 64. You can ask whether a variable is of a certain type with isa. To convert a value x to another type t, use the function with the name convert t, x. Often this can be simplified to, but of course, this conversion will not always succeed. The following produces an error. Julia is specifically designed for computing. No wonder it has a wide range of number types. All types of mathematical functions are defined on them. like logarithmic and calculus functions. Often, we need to represent a range of numeric values, and Julia has the type to do just that. A range can be constructed with a colon operator or with the range function. Range bracket 1, 10 close bracket contains 1, 2, 3, and so on, including 10. A step can also be specified. Julia char type takes 32 bits, so all Unicode UTF-8 symbols can be represented. In Jupyter Notebook, we can also represent non-Western characters correctly. Julia is also well equipped to deal with strings. The variable species1 contains a species of the iris flower family, as do species2 and species3. They are all of type ASCII string. If the string contains non-ASCII characters, it is of type UTF-8 string. Does this remind you of the Isis flower dataset? This dataset contains some length and width measurements of the 3 species, and we use it throughout the rest of the course in concrete examples. See the link for some introductory information. Strings can be considered lists of characters, so by indexing a string with an integer, you get a character. Notice that Julia starts indexing from 1, not from 0, as in C and many other languages. Indexing with a range returns a substring. Also, note that strings cannot be changed through their index. To produce formatted output, all print functions support what is called string interpolation, like in this example, $species1. The content of species1 is substituted by line 78. After the $sign can come any variable or expression between parentheses. Another possibility, which allows for C-style formatting, is to use the @printf macro. We will come back to macros and why they are so useful in video 2.3. You can recognize them because they start with the @sign. Another string-like type, very useful to represent labels or categories, is the symbol type. You can make a symbol by prefixing a string or character with a colon, like this. A string is a collection of characters, and as such, we can loop through it with a for-in loop. This is also the case for other collection types, which we will encounter next, like arrays, dictionaries, sets, and so on. Let's check the code in Sublime Text. Here you immediately recognize the comment sign hash with the output of the for loop. We can execute the code with Ctrl-B, or Shift and Enter in Jupyter, or from the command line as julia filename.jl. Again, an enormous wealth of functions exist to work on strings. We demonstrate a few of them in the REPL. Suppose you need the index on which the dot character starts in the string species. Use the search function. Julia offers the complete regular expression syntax to match patterns in strings. If you need to split a string on a space character, use the split function. The result is an array, in this case with 2 elements of type, substring ASCII string and dimension 1. Array is exactly the type we will now discuss. Arrays are the workhorses in Julia code. They group together items of the same type. Let's take a look at some examples. Again, they are indexed starting from 1. That means that the length of an array is equal to its highest index, which is quite refreshing. We can take a slice of an array like this. Contrary to strings, arrays can be changed by index. You can make an array from a range with the collect function. Here, we initialize our arrays. We can also create them empty, or use the push function to add items, like this. Whenever you see a function ending with an exclamation mark in Julia, it means that the object itself, in this case, R2, is itself changed. You can also create arrays with random elements, with the rand and randn functions. For example, randn5 generates an array with 5 random floating point numbers. normally distributed with mean 0 and standard deviation 1. As you might expect, we can loop through an array with 4 in. If our array contains elements of different types, Julia infers that its element type is any, like in this example. Over 300 functions or methods exist to work with arrays, like min, sum, pop, sort, and so on. You can look them up in the website docs. We'll revisit some of those in video 1.7, when we talk about matrices. In this video, we have learned how to work with data in variables. We talked a lot about arrays, because these are very common in data science code. In the next video, we will explore how to write real code in Julia that represents a certain action or decides on conditions. Hello again. In the previous video, we learned how to work with Julia's simple data structures. In this video, we are going to take a look at how to manage the order of execution for Julia code. We'll investigate expressions and common ways to structure code, such as if, while, and for. You also will learn how to catch an expression occurring in your running code. Julia allows us to initialize several variables all at once, like this, or like this. Also, we can make different statements in one line, but then we have to separate them with a semicolon. This compound expression calculates the area of a circle with radius r3. R is squared here, and the opened and closed brackets only serve to make the statement clearer. Instead of using semicolons, we can also spread those statements over different lines, provided we enclose them with a begin-end block, like here. X gets the value of the last expression, a plus b in the block, so it becomes 5. This tells us that Julia is pretty flexible. Controlling the flow in Julia code is not much different from how it is done in other programming languages, like Python. Compared to R and the C style, it is much more readable, however. No parentheses around conditions are needed. No curly braces. A block of code simply ends with the word end. To test one or more conditions, there is of course an if construct, like in this example. The resulting value of a branch in the condition can be assigned also, like in this example, where max gets the value 15. This can be abbreviated to the so-called ternary operator. If the value of the expression before the question mark is true, then the expression on the left of the colon is calculated. Else, take the expression on the right. Simple, right? To repeat the code based on whether a condition is true, use a while statement, like in this code, where increase year is printed as long as the year has not reached 2050. If the loop has to stop in 2047, we use a break. We also have a continue statement to start the next loop iteration. And of course, a while true loops indefinitely. End the loop with Ctrl+C. We already encountered the for loop in the previous video. In general, for is used to loop through a collection, like an array. Here, the variable blg captures the value of the array, blood groups items one by one. If you also need the index, use enumerate like this. If you just want to use a fixed number of times, use the same form with a range. You will notice that sometimes your running program encounters an exceptional condition, like a file that must be opened, but does not exist. In that case, the program will crash with a system error, like in this example. There are some 20 built-in exceptions in Julia. For a list, see the docs. You can also invoke an exception yourself with throw, like when a code is not one of a number of known blood groups. But it is probably better to just use the error function, where we can give our own message about what went wrong. And, if you would like, we also have the warn or info function at our disposal, which will not let your program crash. We can also prevent the program from crashing by encapsulating the open command in a try block. A possible exception will then be caught in a catch block, and the program will continue after the block. We have seen quite a few error handling mechanisms, right? Julia also makes available a system for starting different code blocks simultaneously, called tasks. The main code can continue executing, while a scheduler runs the tasks in one thread. Here is an example. @async is a macro that starts a task independently from the main running code. It could potentially start up a long-running calculation. Consume will wait until the return value of the task becomes available. Tasks do not run in parallel, but they can still be useful to make your code more responsive. Through this video, we now know how to structure code execution with if constructs, and while and for loops, and how to handle possible errors. We also briefly discussed how to start independent code tasks. In the next video, we'll build on this knowledge to isolate code in separate functions. Hi, in the previous video we learned how to structure our code through testing of conditions and repeating blocks of code. But all the code until now was top level or global scope as it's called. We never called code from a function. Using functions not only is best practice, but also allows Julia to optimize execution. In this video, we're going to take a look at functions, how they are created and used in Julia. We know that Julia is specialized in computation and data manipulation, so it comes as no surprise that functions are extremely versatile. As we will see, Julia is very much a functional language, with powerful map, filter and list comprehensions. We also investigate the importance of using types in functions. To start simple, here is a function that takes 3 arguments and returns their sum. Notice how Julia responds with sum, generic function with one method. Functions in Julia are generic. That is, they work for a lot of argument types. For example, as a side note, be careful in a code file. A function must be defined before it can be called. Otherwise, you get a load error. The keyword return is optional. A function always returns the value of its last expression. That could also be multiple values, like in this function. A function also has a type, function. We did not have to indicate the type of the arguments, but giving arguments of a random type will not work most of the time. Like when trying to calculate the sum of a string and an integer and a boolean. Julia tells you you cannot sum a string and an integer. So, indicating the type of the argument is often not only sensible, it will also give the compiler more information to produce better optimized code, although the compiler is often intelligent enough to do this automatically. This can be done like this. The function specialized for an int64 argument now counts as a second method. A method is nothing more than a function where the types are indicated, or, in other words, one possible behavior of a function. So, a good rule of thumb is to define the types of arguments whenever you can and however precisely you can. If we need to indicate a type of a variable in code, but this can only be done local in a function, like p in the function sump. If you want to type less, you can do so if the function only contains one expression, like this. Sometimes the number of arguments can vary from call to call. In that case, use the splat operator, 3 dots, which takes in a variable number of parameters into an array, here named args. As you can see, this also works for 0 parameters. Functions also can have optional arguments, like n3 in this example. In that case, n3 has to have a default value, here 5. If you prefer to indicate a parameter by name, use a keyword argument like n4. They must appear after a semicolon and also need a default value. Try out different combinations for yourself. Our original sum function can even be written shorter without any name, as an anonymous function or lambda expression, like this. This notation becomes useful only within another function, as we will show in the following example. Suppose we need to simulate 100 measurements with values between 0 and 1, and then square each value. The rand function gives us the measurements. To square them, we use the lambda syntax, combined with a map function, like this. Map applies the anonymous function to every element, x, in the array, r, and returns the resulting array, r2. But map is also a function. In Julia, a function can take other functions as parameters. A function can even return a function. But we can write this even shorter with a list comprehension. This builds an array by applying the expression x squared to every element in R. You'll agree that this syntax makes for very elegant code. Another handy built-in function allows us to filter elements according to a criterion. The following code first defines a function is odd to get uneven integers, and then we filter the odd numbers from a random sample of 100 numbers. Or using the lambda syntax. Julia also has a reduce function, and folding functions fold L and fold R, even in combination with map. Do look it up in the docs. Let us now investigate the performance of code and functions. We take a random number and its sign value, sum it to a result value, and execute this 1,000,000 times. The underscore is used here as a separator. To simplify this, we will put the code in files. First, the code that does not use a function in file 15glob.jl. We can execute this file in the REPL by typing Now that the code has run once, we are ready to measure it. This is done with the @time macro, like this. First, we see the result, then the time it took, 0.35 seconds. And then the memory it used, nearly 92 megabytes. We also see the amount of garbage collection, GC, that Julia has done to free memory. The first time Julia code runs, it compiles, and then the compiled code is cached in memory. That's why performance must be measured after the first dry run. Now let's put this code in a function which returns the result in file 15func.jl. The same way, we get... Not only did this version use 1/3 less memory, it was 5.6 times faster. But wait, we can still do better. Let's change the initial value of result from 0 to 0.0 in file 15func.better.jl. This time, we see that the code executes 2.4 times faster, but it did consume 25,000 times less memory, and no garbage collection was needed. Why is this? The variable result was previously given the integer value 0, but the calculations need floating point values. For that reason, Julia can't optimize the generated code fully, for execution time and memory usage. When results starts out as a floating point number, the code is fully optimized for floating point calculations. This is an example of type stability. All computations take place with the same type, which maximizes execution speed. So, pay attention to types. Using the right type in values and type indications can make for much faster and performant code. In this video, we saw how working with functions can be versatile and elegant. Also, the importance of using type-stable functions for performant code was illustrated. In the next video, we'll add a few more tools to our data structures belt, which come in handy when exploring data. Hi again. In the previous video, we learned how to use functions in Julia. The only data structure that can contain many elements we used until now was the array. But arrays can only be accessed by index, and all elements have to be of the same type. In this video, we're going to take a look at more flexible data structures, such as tuples and sets. In particular, we want to store and retrieve data by key, as is possible in dictionaries. Tuples can contain elements of different types, unlike arrays. Variable t1 is an example. Its type is a tuple of these types of elements. Tuples are not new. We encountered them implicitly as the argument list of a function, or when a function results more than one value. Tuples can be unpacked, like in this example. A swap of variables is possible in one line thanks to tuples. Tuples can be indexed. As with every collection, we can loop through them with for, but unlike arrays, tuples cannot be changed. An array or a tuple do not check whether the same element appears more than once. If you want unique elements, then a set is your friend. We make sets like this. If your set contains different types, use any, which is the most general type in Julia. As we can see, sets only retain unique elements, but unlike arrays and tuples, they don't keep the order of the elements. Operations on sets include union, intersection, set diff, and is subset. For example, intersect S2 produces a set with a single element, 11. Wouldn't it be nice if you could just store and recall a data value based on a key other than an index? That's exactly what the dictionary type offers. Here is an example that gives us the frequency of each iris species in the iris dataset. As the last part of this video, we will show you how we calculate this. But for now, let's concentrate on dict basics. We can see that a dict contains key-value pairs, where the key is separated by an arrow from the value. In this case, Julia infers that the key type is ASCII string, and the value type is int64. The only restriction on keys is that they must be hashable. That is, an integer hash code can be calculated with them. Often, it can be convenient to convert string keys to symbols, like this. Notice that the pairs in a dictionary are not stored in key order. The value corresponding to a certain key can be retrieved like this. In the same way, you can change the value. You can detect whether a key is present with hasKey. The keys and values function, respectively, gives us two arrays, one with the keys of the dictionary, one with the values. Being arrays, we can go through them with a for-in loop. And if we need both key and value, that's just as easy. Now, as a concrete project, we show you how to calculate that dictionary based on the file iris.txt. The first lines of that file are shown. We are going to calculate the number of times each species, like I-setosa, appears in this file. You can find the code in file 16countingflowers.jl. In the first part, we get the input and start processing. We read the data records from the file. We will cover this in detail in section 3, video 1. But I think you can easily understand the code. The file is opened. Each line is read into a string called line. We then extract the species name from the data line, removing trailing spaces, and put it into our array, iris. The do block automatically closes the file after the loop. In the second part, we make an empty dictionary, species freak. We loop through the iris array, and for each species name in the array, we ask if an entry with that key already exists in the dictionary with hasKey function. We could have used an if-else operator here, but the ternary operator makes for more elegant code. If the entry already exists, its value, which is the count, is increased by 1. If not, its value is set to 1, thereby creating that key value pair. In the third part, we collect the key values into an array, which is then sorted. We loop through the array, printing the key values now in sorted order, together with their frequency. Congratulations! You just made your first complete Julia project. In this video, we have explored tuples, sets, and especially dictionaries, and seen how they can be made useful in a counting project. In the next video, we will learn how to work with matrices. These are in fact two-dimensional arrays, so we already know a lot about them, but there are still nearly endless possibilities we haven't explored yet. Hi, in the previous video we learned how to use tuples, sets and dictionaries. In this video we're going to take a deeper look at matrices, because a lot of calculations in data science and machine learning are done within matrices, and it is one of the great strengths of Julia. Moreover, data is often presented in two-dimensional matrix form, with rows and columns. We'll see how to construct matrices, work with them, and how to apply functions on them. We know that 1, 2, 3 creates a one-dimensional array, or vector, in fact, a column vector. How do we create a row vector? Simply by replacing the commas with spaces, like this. In fact, we see that Julia considers this to be a two-dimensional array, or matrix, with 1 row and 3 columns. To construct a matrix with more than 1 row, use a semicolon after each row. In this example, we have 2 rows, as given by size, MA1, and 3 columns, given by size, MA2. The number of dimensions is n dims, MA. EL type gives you the type of elements. Julia has lots of ways of creating matrices. For example, rand, to create matrices with random elements. I, a matrix with all zeros except ones on the diagonal. Or, how about creating a matrix with a list comprehension, like this? How can we access specific elements, or specific rows, or columns, or even subparts, or slices of a matrix? In the examples we use, the following matrix, MA, an element is accessed by its row and column index, like this. A colon can substitute for all rows or all columns. MA 2 colon gives all elements for row 2. MA colon 3 gives all elements for column 3. This example takes this second and third columns from row 2 and 3. MA1 colon 2, 2 colon 3 takes the second and third columns from rows 1 and 2. N can be used as the last index in every dimension. For example, like this. To change or set elements, just use the same notation at the left of the equal sign in an assignment. Here are some other useful ways to build matrices. For example, we start from matrices A and B defined as C equals square bracket A, B, close square bracket, or H cat, open bracket, A, comma, B, close bracket, glues B onto A horizontally. C equals open square bracket A semicolon B close square bracket, or vcat open bracket A comma B glues B beneath A, making a new matrix C. That is, vertically. The reshape function can come in handy when you want to change the dimensions of your matrix, like here. This will only work when the number of elements matches the product of the new dimensions. You can calculate with matrices like this. A plus B sums them element by element. A star B calculates the matrix product as defined in mathematics. If you want an element-wise product, do A dot star B. This dot notation is always used to indicate that the operation must be performed element by element. You can do operations with matrices and numbers like this. To transpose a matrix, use the tick operator. The inverse of a matrix, if it exists, is calculated with inv function, so that a star inv A produces an identity matrix with all zeros and ones on the diagonal. Let's now get back to our IRIS database. Here we see the first of the 150 records in the file, iris.txt. The first 4 columns represent the measurements on a specimen of the species indicated by the last column. They are respectively sepal length, sepal width, and petal length and petal width in centimetres. These are our 4 features. The columns form a matrix on which we could do some useful calculations. Because the dataset is already ordered, lines 1 to 50 is iris setosa, 50 to 100 is iris versicolor, and 101 to 150 is iris virginica. We can connect calculations to the species. But first, we have to extract this info as a matrix variable, which we will call lengths. Here is the code to do this. In line 9, the lengths matrix is created. In the for loop, in the open block, we cut out the first 4 columns as a string m lengths in line 15. In the following line, we split this on the spaces to an array of strings, which in line 18 is converted to an array through a list comprehension. We transpose this array and append it to lengths, with vcat in line 21. Lengths is now an array of type array float 64 2, with dimensions 150 by 4. We can calculate the total sum, the sum of each column, and the sum of each row as follows. This is not very useful because we can't discriminate between species. For that, we must create a separate matrix for each species, which we could do as follows. The means for every feature is given as follows. So, we learn, for example, that the mean petal length for I setosa is 1.462 centimeters. To get the smallest and largest value for each feature, we can do. These and other possible calculations are nice, but somewhat tedious. In videos 3.2 and 3.3, we will explore the same dataset as a data frame. Julia's workhorse for the data scientist. With DataFrames, more useful info can be extracted much more easily. In this section, we explored the basic data structures in Julia, from numbers and strings to arrays and matrices, dictionaries and sets. Controlling program flow in Julia was also covered, as well as functions which are the basic building blocks of Julia code. In the next section, we will get more experience with Julia and gain insight of how Julia is built. The importance of types is stressed. We will show you how to use modules and write macros to better organize code. Lastly, we will show how to install, use and manage packages through Julia's built-in package manager. Hi, and welcome to section 2, diving deeper into Julia. In this section, we will further discuss the use of types to make code more general and performant. Using macros to make code more flexible and less repetitive will be discussed, as well as modules to organize code. Finally, we explain how to add the capabilities of your Julia environment by using external packages. Now we move on to the first video of this section that deals with types and parameterized methods. We'll gain insight into the overall importance of types in Julia in writing generic and performant code. Indication of the type of variables in Julia is optional. A program can run without types, which is useful when prototyping. In fact, Julia infers the types. Typing variables, especially function parameters, can increase performance and make your code more robust by throwing exceptions in cases where certain type operators are not allowed. Julia has a rich built-in type system, and most data can be parameterized, such as these types are for two-dimensional array of floating point numbers of 64 bits, and a dictionary with symbol keys and float 64 values. In fact, we could write this with a generic type indication, like T or K and V. For example, T could be int32, float 64, ASCII string, symbol, and so on. Isn't that awesome? If you need to assert that the value is of the right type, use the assertion operator : in local variables or functions. A type error is introduced here to show how Julia responds. int64 is a concrete type because there exist values of that type, like 108. It has a supertype, signed. Signed is an abstract type because there are no concrete values of that type. Instead, it has subtypes. The less than colon notion is used to indicate that int32 is subtype of signed. In the same way, all number types are subtypes of the abstract type number. Types in Julia form a hierarchical tree, with any as the common supertype. Any has 228 subtypes. You can see part of this tree for numbers on the screen. If you didn't know, a developer can define his or her own types as well. Let us define a type iris for our iris flower measurements. You see, we indicate the type of every field. If you give no type, it is assumed to be any, which means it can be any type. You can get the field names of a type as an array of symbols by using field names. The type definition automatically creates methods to make iris values as follows. Fields can be accessed with a dot notation, as in Java or C#. Such a value is mutable. For example, if I want to change the petal width to 0.3, this works. If you want to forbid that a value can be changed, then the type must be defined as immutable. Note that a type definition cannot be changed in Julia. That's why we must take a different name. You can also make arrays of our iris type and put out measurements in it. We could make our definition of iris more general by specifying that all measurements must be of the same type, T, but T can be any number type that is a subtype of real. We say that iris type is parameterized. Now, measurements can be integers or decimal numbers. In the same way, functions are parameterized when they take a generic type for their arguments, like in this example. Here, we define a function, add, that takes two arguments of a generic type, t, because we know for certain that plus is defined for all numbers. We could even specify t to be a subtype of number. For instance, if we try to add two flowers, we get a method error because plus is not defined for strings. Julia looks at the types of each of its arguments and chooses, dispatches to, the most specific method, the one that best fits all types. This will generate more performant machine code, optimized for these types. That is the reason why indicating types in functions can increase performance. This is called multiple dispatch. Let's check this in our code. Say we define a function to add two floating point numbers, which prints that out. Now we have defined three versions, called methods, for the function add. We can list these with the methods function. When we add two integers, one of the general add methods is called. But when we add two float 64 numbers, the add method specific for this type is executed. Every function or operator, which are also functions, has a number of implemented methods. Look at the plus operator. It has 171 methods in Julia v0.4, defined for all application types. Suppose we would have defined a different type for each of our iris flowers. We could then define a union type iris that unites them all, and define methods that take an iris type. These would work for all flowers of types setosa, versicolor, and virginica. Any values of these types is also of type iris. In this video, we have investigated types in Julia and saw how they can be used to make methods and user-defined types more general. In the next video, we will learn the use of modules for our better code organization and structuring larger projects. In the previous video, we got more insight in the importance of types in Julia. In this video, we're going to take a look at macros, why they're useful in making shorter, more elegant and less repetitive code, how macros work, and how you can make your own macros. In video 1.5, we studied functions and also used our first macro, @time. Here is another example of its use. We define the factorial function using ternary operator form of if-else. We print out the result of calling this function for value 20 with the macro @printf. Then we measure its time and resource usage with the macro @time. So a macro call looks like a function call, but it starts with an @ sign. In the code of Julia, macros are used all over the place. We can use real macros like in the famous Lisp language, because Julia is based on the same underlying principle, which is code is data, also called as homoiconicity. In fact, the first stage in Julia parsing is done by a Lisp interpreter called femto-Lisp. As you can see in this screen, because of that, we can change code during the stage when Julia code is parsed, but still before the code is executed. This is precisely what macros allow us to do. Before we can build macros, we need to elaborate on some basic concepts, like expressions and evaluation. We already met this symbol type represented with a column prefixing a name. With :n, no value is shown. The colon stops the evaluation of the variable. This is true for expressions as in this example, where the sum of two variables is stored as an expression in variable e, which has type expr. The function eval computes the expression. Eargs gives the constituent symbols of the expression, the operation plus, and the variables a and b. Code highlight. If there is one more line in the expression, it is easier to use quote, end, but this is exactly the same as the colon operator. Variables can be interpolated in expressions with $, just like strings. We can see it in this example. Let's now make our own version of the @time macro. We'll call it timeIt. It won't be as accurate as @time, but we'll learn a lot from it. Here it is. A macro is defined between macro and end. TimeIt gets as argument an expression or a function x. We pin the start time t0, then execute x with $x, and then pin the end time t1. We declare all variables to be local so as not to interfere with outside variables. The esc function makes sure x is pasted literally in the generated code. Then we print the difference in time and return the computed value. When called with @timeIt fac20, x becomes fac20, and the code between quote and end is substituted into the rest of the code. After that, all the code is executed. So you see, it's not that difficult. Let's now build a macro called repeat that repeats one or more instructions a specified number of times. For example, print out "Hi Julia" 7 times. Or execute for a loop 3 times. The macroExpand function lets you see the code that will be generated, which is very useful for debugging purposes. The value of the args field of expressions are also often used in macros. A macro looks superficially like a function, except macros do not evaluate their arguments when they are dispatched. They treat their arguments as if they were quoted expressions. Macros return expressions. Those expressions are then evaluated in the environment that called the macro. If a macro is used inside a function, it is executed when the function is defined, so before the function is compiled or run. This should convince you of the usefulness of macros. Here are a few useful macros defined in standard Julia. @assert. Test a condition and throws an assertion error when the condition is false. This is useful to test preconditions in functions. For example, whether an argument should be a positive number. The base. Test module contains a macro @test, which behaves like @assert, and @test_approx_eq, which tests if 2 numbers are equal within the machine range. 2 and 2.1 are clearly not approximately equal. But @test_approx_eq EPS lets you specify as a third argument the difference range. 2 and 2.1 are within range of 0.15 of each other, so no error is printed. The macro @Windows returns true if you are on a Windows machine, so you could execute some code only if this is the case, or not. Similar macros @OSX and @Linux exist for other operating systems. If you have an expression and you want to look it up in Julia's source code how this is executed, use @which. For example, here the macro tells us that the multiplication of complex numbers is defined starting on line 113 in the file complex.jl, which resides in the subfolder /share/julia/base of the installation directory. Find out more about all built-in macros in the help mode. In this video, we have learned how to use the macro facility in Julia, using built-in macros as well as developing our own. In the next video, we'll look at how to structure your code into a module when your project grows larger. In the previous video, we looked at macros as a way to generate code. In this video, we're going to take a look at how to structure the code of a larger project by using modules. We'll see how to make them and the different things you need to know in order to use them. Until now, we have made a few types and functions to work with iris data, scattered in different files, but the code is more organized when we bring it together in a module, sometimes called namespace in other languages. For example, we call this module iris tools and put its code in a file iris_tools.jl. The code must be between module iris tools and end. In order to use this code in the REPL or in another Julia script, like use iris_tools.jl, we do the following. Include the code file. Do a using iris tools. Variable fname is still unknown, but variable species is known. Why is that? Because we have performed export species. Every definition in a module that you want to be able to use outside that module must be exported. After the using module, an exported variable, function, or type is known in the global namespace. If I want to force the use of an unexported definition, I can do an explicit import, qualifying the definition with its module name. Or alternatively, you can do an import iris tools and just use the fully qualified version iristools.fname. If you change the source code of an imported module, then do the following. Clean the memory of the REPL with workspace. Include the module again and do a using. Now the changes are loaded. We can now call, for example, the read file and counting species functions to obtain the counts of the measurements for each species. If we export type iris and define a show method in the module as this, then we can call this method as you can see on the screen. In Julia, you can document functions with markdown strings between double quotes or triple quotes in the lines above the function. Then, when working in REPL, you can ask for the documentation for the function in the help mode, like it is shown here for the counting species function. A module can also consist of different files. Suppose the code is distributed over the files irisvariables.jl, iristypes.jl, and irisfunctions.jl. Then we could construct our module in a file iristoolsf.jl as follows. But what if two modules we want to use have a function with the same name? For example, the graphics modules, Winston and Gadfly, both have a plot function. For the following code to work, we first have to install both packages with pack-add Winston, pack-add Gadfly. But how does Julia distinguish between the two versions of plot? If you import both modules, you can use each plot function in its fully qualified version. So it is clear from this example that each module defines its own namespace for the definitions it contains. If we import all exported definitions of Winston with a using Winston, then the plot function from Winston can simply be invoked by plot. If we then do the same for Gadfly, we get the following warning for conflicts of names. The existing identifier mentioned here is the plot function from Winston, but we can still use gadfly.plot. The text of the warning in the screen mentions the module main. What is this? Main is a module that Julia creates at top level, whether it is in the REPL or when you start a Julia script. Main contains all created definitions at top level, as well as all exported definitions from modules. The whos function shows you these definitions. Here is its result for a freshly started REPL. Module base contains all code for the standard library. Module core contains all Julia's built-in identifiers, like pi and e. All modules contains an implicit using base core statement. ANS is a temporary variable name for the last result only available in the REPL. If we define a variable a equals 10, whos shows you that variable. After bringing our module iristools into main with include, we see the command workspace we used earlier clears all newly created and imported variables from main. Every module also can contain a init function, which is executed immediately after the module is loaded. In our module iristools, we could call the function readFile in init, since many other functions need this as a prerequisite. The variable loadPath contains a list of directories where Julia looks for module files when running the using import or include statements. It can be set up at the operating system level as julia_load_path in a startup script such as .bashrc or .profile, or in the environment variables on Windows. You can also extend this variable in code using push!! In this video, we have learned how to use modules and seen why they are useful in larger projects. In the next video, we will learn how to use the modules written by other developers in the Julia package ecosystem. Hi, in the previous video, we looked at how to structure our code in modules. In this video, we will learn how to work with Julia packages. Often functionality that you need in your project is often already written and exists as a package, which is Julia's name for a library. We will look at how to search, install, and work with packages to enhance your own projects. Julia's standard library is very rich in mathematical functions, but often you will want to use an additional package to enhance your project. In fact, we already did so in section 1.2 when we installed iJulia for working with Jupyter notebooks, and in the previous section for the packages Winston and Gadfly. On package.julia.org, you can find an alphabetical listing of all officially registered packages. These packages are contained in the official central package repository, which lives at github.com/julialang/metadata.jl. But there is also other Julia packages on GitHub, such as sqlite.jl. Julia's installation contains a built-in package manager, PKG, for installing additional Julia packages written in Julia. The downloaded packages are stored in a cache ready to be used by Julia, given by pkg.dir, which is located in the .julia folder of your home drive. So, packages are stored in a central place on your machine, a local repository. This cache, or local repository, is initialized with the command pkg.init. This initialization is done automatically when you install your first package with pkg.add, package name. Let's install iJulia in a fresh environment. As you can see, a whole list of dependent packages is also installed and then compiled. Installing a package also downloads all packages the new package depends on. These are respectively the required packages listed here, and the additional packages are the dependent ones. This is all taken care of by the package manager called PKG. Each package has a version number of the form NML. If you want to check which packages are installed, run the pkg.status command in the Julia REPL to get a list of packages with their versions as shown in this screenshot. Now the package is installed, but to use it in your code, remember to do a using package name. The package is then found automatically in our local repository. The packages we install from the metadata repository, in fact, consist of one or more modules. Their source code is also downloaded locally. It is important to keep your repository up to date with the latest version of the packages. This is done by issuing the command pkg.update, which you should always do before adding a new package. But if you don't want to use a more recent version of a package, you can pin down the version of a package used in your code with the pin command. For example, for the case we want to use explicitly version 0.4.3 of package HDF5, but not later versions. Use the following. Julia packages must be published on GitHub, but perhaps the package you need has been posted on GitHub by its authors, but not yet made available in the Julia Central Metadata repository. In that case, you can fetch such a package with the clone command. For example, to install the An package by Eric Chiang, we would do. In the rest of this series, we will come across and use a whole bunch of specialized and established packages of interest for the data scientist. How should you go about choosing packages? First, look at the version number. 0.0.0 or 0.0.1 denote a package still in its infancy. Also, how recently has there been an update? A year ago or more probably does not sound that good. Then it certainly was not updated for the latest Julia version. Does it contain tests, and did they pass for the latest Julia version? Has the package multiple contributors? The amount of stars also indicates its popularity. Even when the package is old, you can always check out the code and build on it, perhaps to create your own package version. To exercise using packages, let's do some basic graphics plotting. First, we install the Winston package. Here, we plot 100 random numbers normally distributed around 0. which is displayed graphically as this function is displayed as. To conclude, here is the code for a complete example with labels and color display. Here is the display. In the coming videos, we'll use this package as well as other graphical display for our data investigations. In this video, we enlarged our view of the Julia world by learning to use packages. In this section, we now have a deep understanding of Julia. We saw how important types Julia works. We learned the basics of generating code by writing macros. We organized our code in a module, and finally, we integrated packages. In the next section, we will use the specialized DataFrames package to extract and work with data from all sorts of file and database formats. Hi, and welcome to Section 3, Working with Data in Julia. Before we are able to process data, we need to get them out of their data sources and into our Julia program. In this section, we will learn how to work in Julia with data from various data sources, such as structured files, relational and NoSQL databases. We'll use data arrays and DataFrames to store the data within Julia. Now, we move on to the first video of this section that deals with reading and writing data files and Julia data. After this video, you can extract data from all kinds of data files into Julia for further processing. More specifically, we are going to take a look at CSV, HDF5, and JSON files. Furthermore, we'll learn the built-in way to store Julia data to disk with JLD. Already in video 1.6, we applied the basic code for reading and processing a file line by line. The doFile syntax automatically closes the file when finished, so it is better to use this form. Writing to a file is just as easy, as shown in this code snippet, where we have defined a type iris, made an instance iris1 of that type, and written this information to the file example.dat. To append to a file, use the A option instead of W in Open. The file iris.csv contains the same iris data as before, but now the fields in each line are separated by a comma. We can read its data into an array with the readCSV method as shown here. Data is now a matrix with 150 rows and 5 columns, all of type any because no common type could be found. The same result can be obtained with the readDLM method, where you can give the delimiter character as the second parameter. This method is much more versatile, as you see in the second example. The data type can be given the line separator, whether or not there is a header line, with the column names, which are the metadata, and so on. To write to a delimited file, we use the writeCSV method, or more general, the writeDLM method as shown here. Julia also has a CSV package specifically aimed for working with CSV files using the Data Streams interface. I hope you found this easy. Perhaps you have already come across HDF5, which stands for Hierarchical Data Format version 5. It is widely used as a portable scientific data format. It is structured like a file system and has 2 levels: datasets, which are multi-dimensional arrays of the same type. They have the extension .h5. Groups, which are container structures and can hold datasets and other groups. If HDF5 is new to you, here is a link where you can find more information on where it can be used. To start using HDF5 data from Julia, we need to install and import the HDF5 package. This won't be an issue, so moving ahead. The following code shows how you can write to a plain H5 file containing no groups and read from HDF5 format. We use the same iris1 value and store it with the string iris1 as a dataset name. I listed the different possible options on the screen. A group named iris can be created as shown in this screen with g_create. Then we create a dataset with the name dset1 inside this group and give it the value 150. And we also give the group a description attribute. To read this info back, open the file. With the group name as an index in the file, you can retrieve the group data. Then a data set can be read from the group with read. Isn't it pretty straightforward? The dump command on an HDF5 file descriptor gives you a simple overview of the contents. More info can be found in the package documentation here. Let's take a look at the native twin of Julia, JLD. Julia has its own built-in way for storing objects in files with the extension .jld. This is accomplished with the JLD package, which stands for Julia Data. It is in fact a dialect of HDF5, so the commands are very similar. The advantage over HDF5 is that the Julia type of the data is preserved, even the types you defined yourself. Let's see how it works. You give a variable a storage name, species in our code, and then you save it to a JLD file. Whenever you need that data back, you load the file. As we can see, from the return value, all variables are saved in a dictionary with the storage name as a key. So, you can save multiple variables or a complete dictionary. When you don't supply variables, the entire Julia workspace is stored. The same functional syntax using do with read and write can also be used for JLD. If we additionally import HDF5, we can also save in the same group and dataset structure as with HDF5. Julia has a package JSON to parse JSON data files. We have stored some data in iris.json. Here is an example of processing a JSON file. We read in the fill with read all. After some cleanup, we loop through the data, and each record is converted to a dictionary using json.parse. The other way around, the json.json method can convert any dict, like D in the example, into a JSON string. We'll continue to work with the complete iris dataset in JSON format in video 3.5, where we import it in MongoDB. To finish, here is a useful command to download a data file from any URL. Simply supply the URL and optionally a name for the file on your system, like this. In this video, we learned how to extract data from delimited tabular files like CSV. We got to work with the HDF5 format and its native Julia twin, JLD. Finally, we also worked with JSON files. In the next video, we'll start processing our data with DataFrames. In the previous video, we looked at working with data in different file formats. We can work with the data in arrays and matrices, but Julia has a more comfortable data structure for working with tabular data, called the data frame. We'll see how to build and work with data frames, and how to treat the realistic scenario that certain data values are missing, so-called NA values. Up until now, we read data into a matrix, and although this gives us a lot of possibilities, Julia has a more specialized type, more suited to the needs of the data scientist, called the data frame. Similar to pandas, data frames in Python, or data.frame in R. First, we need to deal with the missing data values. Indeed, in contrast with normal calculations, it is quite possible that some data values are missing. Perhaps they were lost or simply not measured. Such values as called NA for not available. They are of type NA type. Data arrays are standard Julia arrays that know how to work with NA values. They are defined in a separate package, so we have to import that. As we can see, when doing calculations, NA contaminates every calculation in which it appears. Let's construct a data array using the @data macro. But calculating the sum or mean of such an array returns NA as a result. How to deal with these NA values? It's simple actually. Just leave them out altogether with the drop NA function, like this. Or safely replace them with a certain user-defined value, here called REPL. We can do this, converting them into an array while replacing the NA values with REPL. Often, a data item is categorical. Its value is one of a small number of fixed values. For example, we could have an array with a potentially large number of measurements of blood type, but the value can only be one of A, B, AB, or O. In that case, we can construct a pooled data array with the @pdata macro or with the pool function. Such a pooled array consumes much less memory than a normal array because it contains only references to the categories. The different categories can be extracted with the levels function. Most real-world datasets have a tabular data structure, like an M(x)(n) table of n features, measured for m objects. Every feature is a column of measurements, all of the same type, and can be represented as a data array. An M(x)(n) table of data is then represented in Julia as a data frame, a package we also have to import. The columns of a data frame are data arrays. Let's switch back to our iris data. We can give the columns a symbol as name, like species, which in fact is the column header. We construct a data frame from data in memory like this. Show gives us a nice output with the column names as headers. So now we know how to put memory data in a data frame and have a clear overview. A simple way to construct a data frame with pre-existing data arrays is shown here on the screen. The names of the arrays become the column headers. Suppose we have another array with data of the same persons or objects, like the blood types. Then, if the measurements have a common ID column, we can join the two data frames into one, like this. The join columns must have the same name, but renaming a column is easy with the rename! function. We can join on different keys, and left or right joins and other types are possible if one of the arrays does not have values of all IDs. Now, we again turn to our iris data, reading them from a file iris.csv. A data frame is like an in-memory database, and as we will see, presents great flexibility in the ways we can work with its data. But how do we read in the data? Stored in the file iris.csv into a data frame. This is done with the readTable method, like this. We added a header line with the column names into the file iris.csv before reading it in. readTable, like the readdlm command from the previous section, has a lot of options. How do we address rows and columns of a data frame? To show, for example, the second column, do or this. So we can use the column name from the header as a symbol to get that column's data. To get rows and columns, we can use the colon operator and the splicing syntax, as we saw for matrices in section 1.7. For example, this gives us all columns for the second and third row or measurement. And we can combine this with the feature names for better specification. Here we fetch the petal length and species from the last 5 measurements. Let's check out some simple functions to quickly explore the structure of the data. The features, in other words the column names, of a data frame can be retrieved with the names function. We like to get a quick feel of the data. This is given by head and tail, which respectively show us the first 6 and the last 6 lines of data. This is also useful to know the data types of the features. This is given by the eltypes function. No surprises here. The numbers are recognized as floating point, and the species name as a string. We'll dig further into the statistics of the data in section 4.1. When we have a data frame in memory, we can write this out to a file with the write-table function, which again supports numerous options, like shown here. Because the species column does not contain many values, we could apply pooling and save memory doing so. To see the amount of memory the variable data occupies, type who's in the REPL. Apply pooling in place to the species column with pool ! Afterwards, we see we saved some 3 kilobytes. In this video, we have seen how data can be elegantly stored inside a data frame. In the next video, we will explore the flexible ways DataFrames offer to search and mold your data. In the previous video, we looked at importing data into DataFrames. In this video, we're going to explore the flexible ways DataFrames offer to search and mold your data. Until now, we got iris data from an external data file. These data can also be retrieved from the package r/datasets, which provides access to many of the classical data sets that are available in R. As always, we first have to import this package. Then we extract the data with the dataset function. Here are the same data, except for the missing I in the species name, and the feature names are written in camel case. We'll use that version in this section. In the previous video, we saw the names eltype and head and tail functions to get a quick insight into a dataset. You can also use the summary function to get a quick idea about the type and size of the dataset you are working with. As is common in data science, we could separate the features, which are the first 4 columns, like sepal length, petal width, and so on, and the labels, the 5th column, as follows. We know already that we can extract a feature, which is a column of measurements, by indexing the dataset with its name. Like here, for sepal width, you can see that the type of the resulting column is a data array, with the element type float 64. We check this with the eltype function. Of course, we can still access columns by index. Data, too, gives us the same data. Subsetting a dataset can be done just like with matrices. For example, we obtain the 2nd and 3rd column of the last 10 rows in this way. End is a special indicator for the last index. Converting a whole or part of a data frame to a matrix is easy. If for some reason you only need to see the distinct values that appear in a column, use the unique function, perhaps in combination with sort. Now, suppose we want to see only those measurements where the sepal width was equal to 3.2. In general, we want to extract the subset of the data that satisfies a certain condition. How do we do this? To accomplish this, we use the .double equals operator, which does the element-wise comparison. Data, sepal width, .double equals 3.2 returns an array of Boolean values, true for data points, where sepal width is 3.2, and false otherwise. Data with Boolean underscore array and colon selects those rows where Boolean underscore array is true. The result set comprises 13 data rows. It is easy to apply a function to all or a number of columns. Just use colwise. For example, here we calculate the mean of each column. To do the same for all values in each row, not so meaningful here, we could use a for loop over the each row iterator. Now, let's return to our complete data set. In it, we have 3 iris species, and we want to calculate characteristics for each species. To do this, we have the by, group by, and aggregate functionality. To split on different species, see how many measurements we have per species, used by like this. The first parameter is the data frame, the second the feature on which to split or group by, and the third parameter is the function you want to apply, which often is in the form of an anonymous function, as in the next example. Here, we calculate the average or mean of the sepal length, data per species. If instead of header x1, you want to explicitly name the header of the calculated value, use the following format. To apply several functions, for example mean and variance, use a do block. To obtain the Greek characters, type respectively \mu and tab, or \sigma and tab in the REPL. Use aggregate to apply a function to all other features. To explicitly split the data set into subsets, use group by. Within the for loop, you can access each subset, sub-df, as shown here. To put each measurement for a specific feature or features on a different line, use stack. Here, we stacked on sepal length. If we would like to stack on several features, use an array with the feature symbols instead. Sorting data is also one of the first things you want to do. To sort the observations on the column sepal width, you do this. Because of the exclamation mark after sort, the variable data was sorted in place. To sort on several features, just add them to the cols array. To sort the first column, simply use. To apply reverse sorting, add rev equals true as second parameter. Here is a more elaborate example, where the data is sorted in reverse species order and sorted on sepal length and sepal width. In this video, we saw how elegant we can work with data in a data frame. In the next video, we will investigate how we can work with data from relational databases in Julia. But if you are more interested in statistics, then you could go straight to video 4.1 and come back later to the remaining videos of section 3. In the previous video, we looked at the many ways data frames can be utilized. Relational databases are an important source of data. Their data is also tabular by nature, stored in rows and columns of tables, which have relations with each other. Data is highly normalized to prevent data duplication. An SQL is used to query and manipulate the data. In this video, we're going to extract data from relational databases like SQL Server and use them with data frames. If you want to get a quick overview of the available drivers from Julia to various databases, consult the JuliaDB website, github.com/JuliaDB. To set the scene, we have created an Iris data database in SQL Server, and we will import the data from the file iris.csv with the Import-Export Data wizard from the SQL Server Management Studio. If the first line in the file contains field names, check the column names in the first data row checkbox. Choose the delimiter character, and then the destination database. The procedure will copy the data in the table called Iris. If necessary, we can change the field names and types. The species name in the fifth column is clearly data duplication, so we normalize this by introducing a table, Iris species. If we draw a diagram of the two tables, this looks like this. The relation is between the primary key ID of table Iris species and foreign key species in table Iris. The standard way of handling SQL databases in Julia uses the ODBC protocol, because ODBC drivers exist for nearly every kind of data source. To use ODBC requires installing a specific driver and configuring a connection string by using an administration interface. In Windows, this is a standard tool in Control Panel. Administration Tools Group. Using the wizard is straightforward. Be sure to take the right ODBC manager, 32 or 64-bit according to your system. Here we view the final screen. The connection has been given the data source name Iris DSN. For Unix and OS X, you can choose between two administration managers, Unix ODBC and iODBC. Julia has an ODBC package that enables Julia scripts to talk to ODBC data sources and import it to your environment with the standard procedure you see on the screen. Now, make a connection as follows. Getting a handle to the connection with variable con enables us to close the connection when possible through disconnect con. If you only need one database connection, this is not necessary, but with several connections open at the same time, you can differentiate between them through this con variable. To launch a query on the first Iris table, you only need to use the query function as follows. Results then has type DataFrame. Here is an example of a join operation. We retrieve two columns for species versicolor. If you want to avoid new line characters in the SQL string, you can use the string concatenation operator, *= to build up the query string, as shown here. If your program has different database connections open, you can specify the connection object as second parameter to the query method, as shown here. If you haven't stored the query results in a variable, you can always retrieve them from con.resultSet, where con is an existing connection. Now we have all the functionalities of DataFrames at our disposal to work with this data set. For example, by allows us to see how many times each sepal length value occurs. This is the first value of each tuple in column x1. Launching data manipulation queries works in the same way. A successful result is an empty data frame. The data has then been changed in the database. As soon as the database connection is no longer needed, close it with disconnect con to save database resources. Another popular and very lightweight relational database is SQLite. It provides local data storage for individual applications and embedded devices, so it is especially useful in the Internet of Things and for analyzing large datasets. Therefore, it is a good alternative to working with large datasets in memory. Installing SQLite 3 is as easy as downloading the binary and unzipping it. In this screen, we start with SQLite 3 on a command line. We import iris.csv with the .import command in a table iris, and we save it in a database iris.db on disk. Our select count * shows we have imported the data. Leave the shell with .ex. Julia has a package for interfacing with SQLite, which we import in the usual way. We then open the newly created database, irisdb, which returns a database handle db. A query is defined on this db variable, and the second parameter is the SQL query. The result res is an array of arrays. Each line of data forms an array. More specifically, a nullable array, which means data can be absent. All fields have type UTF-8 string. We could have avoided this by creating the table before the import in the SQLite 3 console, like this. Let's look up the mean of the petal width feature per species. We construct the SQL as shown. We execute the SQL statement and iterate through the results with a simple for loop. So, we can draw the conclusion that petal width is a clear discriminator between the three iris species. In this video, we have learned how to work in Julia with data contained in a SQL server and SQLite database. Likewise, there is a MySQL and a PostgreSQL package to work with the corresponding databases. In the next video, we will see how to work with data coming from document databases like MongoDB. Hi, in the previous video, we examined interaction with relational databases. Here, we will look at how Julia can work with NoSQL databases. In this video, we are going to take a look at why NoSQL data sources are important. We'll take a closer look at MongoDB and how to work with it from Julia. Then we also take a quick peek at Redis. Compared to relational databases, NoSQL databases scale better and offer a more flexible data model. So they are better in dealing with large volumes in big data context, where the data is often semi-structured. Different types of technologies exist here, ranging from simple key value, over column and document stores, to graph databases. We'll examine in more depth how to work with MongoDB from Julia, because MongoDB is by far the most popular NoSQL document database. Installing MongoDB system is as easy as downloading and unarchiving the bundle. Detailed instruction info is to be found via the link included on the screen. After installation, the bin folder in the installation directory contains the MonGod data server, as well as a number of tools such as Mongo, a client shell, Mongo Import, a tool for importing data, Mongo Dump, a backup tool, and so on. The data is stored in the folder c:/data/db on Windows, /data/db on OS X, and /var/lib/mongodb on Linux, which must exist and must be writable. The MonGod process starts the MongoDB database management system. If you want the database to be in the current directory, start MonGod with the --db path option and dot as value. We have the complete iris dataset at our disposal in JSON format in the file iris.json. The command shown on the screen uses the Mongo Import tool to import these data to a database iris in a collection of lengths. This database and collection are made on the fly. We can check this in a Mongo client by going to the database iris. There we see the collection lengths, which contains 150 documents given by count. The find_one method shows the first document. _ID is a primary key made by MongoDB. Hope you have followed me so far. Now, the MongoDB shell can be used to do queries, like for example, show us the lengths of the first 5 versicolor observations, while hiding the _ID field. It can also be used to add and modify data. We can work with MongoDB data from Julia through the Mongo package. As usual, here is how to install and import the package. MongoDB stores its documents in bson format. This is a comparison JSON format with the indication of types. For this reason, we also have to import libbson. A connection to the MongoDB server is made as an instance CL of the Mongo client type. With it, we construct a value iris_l of the Mongo collection type, mapped to a certain database and collection, respectively iris and lengths. How do we retrieve all documents of species in Virginica? We first have to construct a bson object with a dictionary that specifies the search condition. Then, count gives us the number of documents that fulfills the condition, and find returns a cursor to the collection. We can iterate through this collection with a simple for loop, processing the fields when necessary. By specifying the right criteria in the dict, we can narrow the search. be sure to double quote all field names. Inserting, updating and deleting documents all follows the same procedure. Create a document for insert, update or delete. Call the insert, update or delete method. As you can see, the count verifies that a document was added and later deleted. That's about it. Let's learn a few things about Redis. Redis is an in-memory database and offers a key value data store. Julia has a Redis package to communicate with this data source. After installing and starting up the Redis server, add the Redis package and import it in your environment. Then we can make a connection object and start inserting data with the set method. The keys method shows you all stored keys. Retrieving a value by key is done with the get method. The data are stored on disk by bgsave. To get started with other commands, consult the Redis documentation. If Julia offers no package for your NoSQL data store, examine whether it is possible to use the ODBC package discussed in section 3.4. In this video, we showed you that Julia can work with NoSQL databases. In this section, we have examined the possibilities Julia offers to work with data in external files, relational databases, and NoSQL data stores. In Julia, these are stored in DataFrames, which is a very flexible data structure to explore data. In the next section, we'll dive deeper into the algorithms and plotting techniques Julia has to offer for statistical work. Welcome back. In the previous section, we explored how to work with data from various sources. We now start with section 4, entitled Statistics with Julia. In this section, we will learn how to use the most common statistical and visualization techniques with Julia's statistical packages, such as StatsBase, distributions, hypothesis tests, and Gadfly. The techniques are applied to our well-known Iris database. To get a good overview of what Julia has to offer in this field, visit the Julia Stats website at juliastats.org or this website, github.com/juliastats. Now we move on to the first video of this section that deals with common statistical techniques to get more insight into your dataset. In this video, we talk about the basic statistical functions you need to get first insights in a dataset. We continue to explore our Iris dataset. If necessary, you can import it with read table from our data file. To quickly summarize the data and get an insight into them, we have the describe function at our disposal, which calculates a number of statistical measures for each column. The information given depends on the column type, as shown here. For the numerical column, like sepal length, we get the minimum 4.3 and maximum 7.9. Also, the mean or average 5.84. And the median 5.8 is given, as well as the first and third quartiles, Q1 and Q3. Because the mean and median lie very close to each other, we can derive that for sepal length, there are no atypical small or high values or outliers. We also get the number and percentage of NA values. For a string column, we only get NA information, the length, as well as the number of unique values. To see this on a single column, use the summary stats function. Minimum and maximum can be called separately. Extrema returns them both as a tuple. There exists also separate functions for the basic statistical metrics, such as mean, length, for the number of measurements or samples, median, STD for standard deviation, and var for variance. If the samples have severe outliers, you could trim these off. For example, we can calculate the mean by taking off 5% from each end with trim mean. All these and many more functions, like z-scores and entropy, exist in the package StatsBase. The IQR, interquartile range, is the difference between Q1 and Q3 and is in itself a good measure of the spread. The minimum, Q1, median, Q3, and maximum are also given by the quantile function. Another easy way to get the distribution of a feature's values is the hist function. Its result is a tuple. The first element is the range and corresponds to the edges of the histogram bins. Here, from 4.0 to 8.0, with a bin size of 0.5. The second element is the frequency vector. It denotes the number of items in each bin, so there are, for example, 5 measurements lying between 4.0 and 4.5, and so on. Count map gives us, for every sample value, the number of times it occurs. As such, it is better suited for categorical features, such as species in our case. Proportion map gives us the relative proportions or weights of each category. Each of the iris species is equally represented. The skewness is a measure of the asymmetry in the value distribution, while the kurtosis is a measure of the tailedness of the distribution. The kurtosis is negative here, so we have a low peak with wide wings. If you don't need that many decimals, use the round function as shown here. To see if there is a statistical linear relationship or dependence between two or more variables or observed data values, we use the correlation coefficient, COR. COR ranges between -1 and +1. The extreme values indicate a perfectly linear relationship, while a correlation close to 0 indicates the absence of a linear relationship. Commonly, a status of weak is assigned to values between 0.1 and 0.3, moderate to the range of 0.3 to 0.5, and strong to values above 0.5. We see that sepal width and sepal length are not correlated, but sepal length and petal length are strongly correlated. A measure of how two variables change together is given by the covariance. If the greater values of one variable mainly correspond with the greater values of the other variable, and the same holds for the smaller values, in other words, the variables tend to show similar behavior. The covariance is positive. In the opposite case, the variables tend to show opposite behavior, and the covariance is negative. Julia calculates this with cov function. We see that Julia offers a wide range of statistical measures to apply to our dataset, ranging from calculation of extrema and quartiles to histograms, value maps, and asymmetry and relationship measurements. In the next video, we will start visualizing data with some common diagrams like histograms, scatter plots, and box plots. Welcome to the second video of the section. In the previous video, we looked at basic statistical measurements. Here, we will give an overview of Julia's graphical capabilities for representing data. If you haven't yet done so, add and import Winston and Gadfly into your Julia environment. For basic graphics, there is the Winston package, which offers 2D MATLAB-like plotting through an easy plot XY command, or by creating a framed plot object with more visualization possibilities. Use display from within a script to show the plot in a new operating system window. Savefig can store images on disk in the PNG EPS, PDF, or SVG format. Here, we display the histogram of the sepal length measurements from the previous video. For more information on specific Winston commands, see the docs. The Gadfly package provides ggplot2-like data visualization using data-driven documents, D3, and is very useful for statistical graphs. It renders publication quality graphics to PNG, PostScript, PDF, and SVG, with for the last mode interactivity such as panning, zooming, and toggling. Let us plot the relation between the sepal length and the petal length by iris species. Here is the code. Geom can take on a whole range of values depending on which kind of plot you want, like box plot, density, histogram, line, point, smooth, and many more. The draw command saves the plot in the chosen format. The resulting plot is shown in a new tab in your browser. We can see that there is a clear distinction between the species. If you already worked with the very complete matplotlib graphics engine or with MATLAB plotting, then pyplot is for you. The pyplot package needs Python and matplotlib pre-installed. It works without overhead calling the Python routines from Julia through the pycall package. Look at the pyplot site for installation instructions. Let's draw a histogram of the sepal width data in pyplot. For that, we need the following code. Here is the resulting diagram, opened as a new operating system window. Numerous other plotting libraries are available as you can see on this screen, some of which can be more suitable in certain occasions. In this video, we covered the most important Julia plotting packages. In the next video, as well as in the rest of the course, we present other examples using these packages. In the previous video, we looked at the graphical possibilities in Julia. In this video, we're going to take a look at some specific plots that are useful for data scientists. To visualize the relationship between two variables, we would use a scatter plot. This is a two-dimensional figure in which dots are drawn in a coordinate plane using the values of one feature to provide the horizontal x coordinates, and the values of another feature to provide the vertical y coordinates. Patterns in the placement of dots reveal the underlying associations between the two features. For example, here is the scatter plot of the relation between sepal width and sepal length in our iris observations. This is done through the following code using the visualization package Gadfly. This plot doesn't seem to show much correlation. Indeed, the correlation between the two features is negative, as we already saw in section 4.1. But we have a number of species flowers. How about colouring them differently in a graph? Basically, we want to colour code them according to the species column of the iris data frame. So we've added in our code colour equals species. Now we get this plot, which is a lot more instructive. We see that there seems to be a linear positive association between sepal width and sepal length. The greater the width, the greater the length. This is especially so for Iris setosa, somewhat less for the other species. Indeed, now the correlation, only for setosa, is definitely quite positive. In the base module, there is a linear regression function called linreg that will fit at least squares line through the data values. Then the equation is a plus b times x. Or if we add this linear fit to our plot, which now only shows the setosa values. This plot was made with Winston package and the following code. G-circumflex makes green triangles. Use O for dots. Here is a plot of the relationship between petal width and petal length for I setosa, made with pyplot. As we can see, the linearity is much less convincing. It was obtained using the following code. In the previous section, we already plotted some histograms. Here is another example, this time in Gadfly, for the petal width feature using this code. When using only one visualization package in a script, qualification with the package name, like in gadfly.plot, is not necessary. Remember our discussion of the describe and quartile methods in section 4.1? A box plot, sometimes called a box and whiskers plot, is a simple graphical representation of the info given by quartiles. It displays the center and spread of numeric variables in a format that allows you to quickly obtain a sense of the range and skew of this variable, or compare it to other variables. Here, we display a box plot of the sepal length of all species in our dataset with Gadfly. The one line to produce this is shown below the graph. Each species has its own box plot. The horizontal lines forming the box in the middle of each figure represent Q1, Q2, the median, and Q3, while reading the plot from the bottom to the top. The median is denoted by the bright line. Above and below, we see the extrema, minimum and maximum. We conclude that the three iris species in our study can be clearly distinguished through the sepal length feature. In this video, we have used the most popular Julia packages for drawing scatterplots, histograms, and box plots, providing greater insight into our data. In the next video, we'll delve deeper into distributions and hypothesis testing. Welcome to the fourth video of the section. In the previous video, we looked at graphical representations in Julia. In this video, we're going to take a look at probability distributions, clustering through the k-means algorithm, and testing hypotheses. Julia supports all these through specialized packages. Julia has a distributions package, which provides tools for working with probability distributions. As usual, we start by adding and importing it in our environment. All common and many less common distributions are defined, such as normal, Cauchy, Poisson, Bernoulli, binominal, and tens of others. They are real data types and form a complete type hierarchy. For example, here we make a normal distribution with mean, 10, and standard deviation, 1.5. Rand, n1, 100, takes 100 random samples out of this normal distribution. Using a random normal distribution is so common that Julia has a special function for this, rand_n, generating an array of normally distributed random numbers with mean 0 and standard deviation 1. Here is how we get 1000 random samples of a binominal distribution with 10 trials and a success rate of 0.7. Kernel density estimation is often a useful non-parametric technique for visualizing the underlying distribution of a continuous variable. It basically operates as a data smoothing technique, capturing those important patterns in the data, while leaving out the noise. Julia has a kernel density package, and we apply it here to our sepal width and sepal length measurements. When we plot the density functions with Winston, the red curve, R is for sepal width, and the blue curve, B, for sepal length. What we get is a probability estimate for a certain sepal width or length. You could regard it as a smoothed out histogram. From the scatterplot of sepal width and sepal length in the previous section, we can presume that the data values are grouped according to species. If we plot the petal length versus the petal width, this becomes even more obvious. To further test this, we use k-means clustering, which aims to partition n observations into k clusters. Each observation belongs to the cluster with the nearest mean, serving as a prototype of the cluster. For this, we need the clustering package. We extract and transpose our features as an array, and apply the k-means function with parameter 3 to group the data values into 3 clusters. The result is shown in the plot on the screen, which clearly indicates 3 distinct clusters. The clustering package also contains other clustering algorithms, such as k-medoids and dbScan. In the video 4.2, we plotted sepal lengths of the different species. Although there is an overlap area, there seems to be a significant difference between the mean sepal length of setosa versus the mean sepal length of versicolor or virginica. We can generate myriad statistics characterizing our data, but how do we know whether or not those statistics are telling us something interesting? The answer: use hypothesis tests. Let's use this package to test our statement about sepal lengths of setosa, variable xset, versus the sepal lengths of versicolor, variable xver. We apply the unequal variance t test to both features. This test as null hypothesis h0 that xset and xver come from a distribution with the same mean, against the alternative hypothesis that the distributions have different means. As the test summary indicates, the null hypothesis is rejected extremely significantly, at the 95% confidence level. Note the double negative, meaning that the means of the sepal length of both species are significantly different, with 95% confidence. The two-sided p-value of the confidence intervals, CI, can be extracted separately. A lot of other tests are available in this package, like the one-sample t test, the B test, as well as non-parametric test. Consult the extensive documentation for further information. In this video, we have explored some advanced statistical techniques. The R ecosystem still has a much realm of statistical packages. What if there is an R package you want to use from your Julia program? In the next video, we will see how this can be achieved. Hi, and welcome to video 4.5, entitled Interfacing with R. In the previous video, we looked at somewhat more advanced statistical techniques in Julia, but the data science world contains a huge wealth of libraries written in R, and chances are you want to be able to use these from your Julia code. That's precisely what we'll look at in this video. First, we'll see how to work with R data files. Then, we'll explore the R call package to call R from Julia. First, to get some data very often used in R examples, import and use R datasets. You load datasets using the dataset function, which takes the name of a package inside R datasets and the name of a dataset as arguments. To get an overview of the contents, use the packages and datasets commands. In the package count, we have the following datasets. What if you have data stored in R format, that is, a file with extension .rda or .rdata? You can read these into a Julia dictionary using the read_rda method from DataFrames, as you can see on the screen. The package rcall, written completely in Julia by Douglas Bates, does what its name suggests. Import it with package.add, and then start an embed R environment with using rcall. Then we have a number of bridging functions at our disposal. rprint lets you use R's print functionality. Global env gives us access to R's global environment. For example, here we create a range :z from 1 to 10 in R and print it out. rcall defines a number of types, which are equivalent to R types. Here are the most important ones. For example, here we define an integer vector. Revel sends its argument to the embedded R for execution. For example, here we construct some objects in R. It can also be used to do basic graphics. Always close a call to R plotting with revel dev.off. rcall allows us to evaluate a function in R's global environment. Arguments are inserted starting from the second position. For example, here we call R's plot function to draw a cosine from Julia's objects x and y. rcopy gives us a higher level interface to function calls in R. For example, here we call runIf function in R, which can be used to simulate n independent uniform random variables. Here we make 100 random numbers between 1 and 5, and assign it to the R vector v. Then we let R draw a histogram by calling hist. Here is the histogram. We now examine R's environment with the R function ls. And we see the objects created so far in R. This video showed us how we can call functions and create objects in an R environment embedded in Julia with the package rcall. But use it only if necessary, because most of the tasks can be done in Julia. In this section, we have learned how to calculate statistical properties of a dataset, how to plot these and other relationships between variables in different ways, how to work with distributions and test hypotheses, how to call R code from a Julia script. In the next section, we will explore the use of a number of machine learning techniques using Julia. In the previous section, we explored the use of the number of learning machine techniques using Julia. Welcome to the last section of this course, entitled Machine Learning Techniques with Julia. In this section, we will prepare data and discuss the general cycle for applying a machine learning algorithm. Then, we will successively apply the decision tree algorithm, a generalized linear model algorithm, and a support vector machine algorithm, all on our iris data. Now, we move on to the first video of this section that deals with the basic machine learning techniques. In this video, we're going to take a look at some basic functionality needed for doing machine learning in Julia. More specifically, we'll discuss how to set up a training and test dataset, preparing data and checking model performance using the ML-base package. When trying to model a dataset, data scientists divide the data into a training dataset to build or train the model, and then apply the model to a test dataset to predict a target variable. This way, the model's predictions can be compared with real data to see how good it is doing. In other words, how accurate the model is. In our iris case, we have 150 measurements of 4 features, or independent variables, and 1 label, or target, or dependent variable, the species. Often, a dataset already shows some ordering, and ours is sorted by species. If we take the first 100 measurements for training, then we would be excluding the observations from a whole species, which is clearly not good. So the training set should better be a randomized part of the whole dataset. We do this by constructing an array called train, of the same dimension as the dataset and filled randomly with true and false values. We filter the dataset with it, like the instance portrayed on the screen. If the value for the row index is true, the row is taken, else the row is omitted. The test data set are now the train rows. Remember, exclamation point is the not operator in Julia. To get an array with random Boolean values, we can use a random sample of a Bernoulli distribution, which gives us ones and zeros, and compare these with 1, like this. Great! We can now systematically describe the steps of building and applying a model like this. Build the model. Optionally, prune the model, making it less deep or complex. Print out the model. Apply the model to predict on test data. The variable predictions contain the predicted labels of the testing dataset. We will encounter this cycle over and over again in the next sections when applying real models. Many modeling techniques use the same schemas and concepts, so it seems natural to extract these into a basic machine learning package. In Julia, the ML-base package was created exactly for that reason. You can see an overview of its topics on the screen. It provides the basic techniques needed for data science and machine learning algorithms, containing more efficient algorithms and types to perform vector and matrix operations. Add it to your environment as usual. ML-base contains the label map type, and derived functions associate a set of discrete string values with integer values, like illustrated here with our species names. Label encode then shows the mapped indices when working on an array with the original names. And group indices shows the indices of the respective labels. Classifying the performance of a model by comparing some example, predicted, values to the GT, the ground truth or real values. Values is also possible. We first have to apply label encoding to our arrays, GT and pred, which is needed because the correct rate and error rate functions need that. Then we can compare them with the correct rate and error rate functions. These use integer values, so we need our label encoding here. We can also calculate the confusion matrix, which shows how accurate the predictions were. Given the three classes in our example, the values outside the diagonal represent the errors. So we see that one virginica was predicted as a setosa, and one versicolor was predicted as a virginica. The performance of a model is often verified by the Receiver Operating Characteristics, ROC. ML-base gives us quite a comprehensive number of ROC functions. For example, here we see the basic ROC applied to our example. All kinds of values, like the true positive rate and precision, can be calculated. We'll apply ROC to a decision tree model in section 5.3. A model is often tuned by setting the design parameters in advance, using a validation dataset. For this purpose, ML-base contains the grid tune method. In this video, we explored some basic techniques useful in many data science or machine learning models. In the next video, we'll talk about classification by applying decision trees. In this video, we're going to take a look at applying different decision tree algorithms in Julia, working on our iris dataset. Decision trees and rule learners are probably the single most widely used machine learning techniques. Let us first explain how this technique works. As a powerful classification algorithm, they can be applied to model almost any type of data. The models are easy to understand and interpret, and they can be readily extracted and implemented into any programming language through nested if-else statements for use in production environments. On the screen, you see part of a decision tree applied to our iris dataset. On the basis of a tree-like set of decisions, the sample measurements are divided or partitioned into groups, represented as rectangles. For example, is petal length less than or equal to 2.45 centimeters? True goes left, false goes right. The goal is to get as homogeneous groups in the end or leaf nodes as possible. Here, meaning that the samples belong to one species, as indicated by the values array. The rightmost node contains 0 setosa specimens, 1 versicolor and 45 virginica, which is quite a homogeneous classification, so entropy is low. Let's make such a classification with the Julia decision tree package, which is based on the ID3 algorithm. We set the scene by creating the iris dataset and separating the features and the labels. Then we import the package decision tree. First, let's apply a so-called pruned tree classifier. The model is created with the buildTree method. Then, pruning is applied to obtain more homogeneous or pure groups. Here, we want 90% or more of a group to belong to one species. This results in a tree with a decision depth of 5, resulting in 8 leaf nodes. We ask the algorithm to explain its model with printTree. You clearly see the 5-level depth and the 8 nodes, which are almost completely homogeneous. The petal length is the most basic decision, and we could have already derived this from our petal width versus petal length plot in section 4.4. But we see that the algorithm delivers us a much more intricate decision tree. Feature n here points to the nth column. For example, feature 3 is petal length. Threshold is the dividing value of that feature, meaning we split into values smaller and greater than the threshold. As an example, feature 3, threshold 3.0, divides into 2 branches. L is the branch where the petal length value is smaller than 3.0, which results in the complete setosa group. R is the opposite branch, where the petal length is greater than 3.0. By lowering the depth level, for example to 3 levels, we get a simpler view of the tree. But not all data points are classified yet. For that, we need the model to its full depth. Now, we can apply the learned model to given feature measurements, predicting the label, species, from these measurements. We can now use cross-validation, or in short, CV, to get a better estimate of the generalization error on new unseen data. For example, for 90% purity and 3 folds, we get this outcome. 3 folds means the dataset is partitioned into 3 equal-sized samples. In turn, 2 of them are used for training and 1 for testing. In scripts, we could use the @test macro from base.test to check for the accuracy. @test only reports an error when the test fails. To try to improve the prediction capabilities of our model, or in other words, the model's accuracy or performance, we can apply adaptive boosting. In this technique, many decision trees are built and the trees vote on the best class for each example. Combining the relative strengths and weaknesses of different trees can lead to better performance. Compared to the build tree method, we only need to add 1 parameter, which is the number of trees to take into account. For example, taking 10 trees or iterations produces this output. Now we can apply this model to test data and get a measure of its accuracy for 3 folds with this function, producing this output. We see that the mean accuracy has been lowered to 0.85, so in the particular case of the iris dataset, this boosting technique gives us no improvement. Perhaps because some of the noisy data or outliers. Decision trees have a habit of overfitting their training set, especially when we require higher depth of decision. Random decision forests can correct this by constructing a multitude of decision trees at training time and outputting the class that is a mean prediction of the individual trees. Here, we use 2 random features, 10 trees and 0.5 of samples per tree. And here is our output. The mean accuracy has now risen from 0.94 to 0.97, so random decision forests are clearly an improvement here. In this video, we have learned how to use decision tree algorithms on data using Julia. In the next video, we will go through a more realistic scenario of training, testing, and plotting our model's predictions. In the previous video, we looked at decision tree algorithms, applying it to our whole dataset. Now we will, in a more realistic setting, train and test such a model. We will first divide the data in a training set and a testing set. Then we'll construct the decision tree model. Finally, we'll test the performance of our model by comparing predictions with actual data. Let's build a model with a training data set and make the predictions for the test data set. We construct a random array with true and false values, as explained in section 5.1. Then we'll filter our labels and features data with the true values, obtaining the training data. For this, we'll build our model with build tree. Then we prune it to remove outliers. Here, 0.7 means that 70% or more of a group have to belong to one species. Notice that the generated model can vary each time we use a new training dataset. Printing out the model tree gives us this result. Look at the leaf nodes to see the results of the classification. Now, with test equal to not train, we obtain the test data. We use these to apply the model and get our predictions for these test data. In our case, the prediction is, given the different length measurements, what will be their species? We apply the label to our data with label map, a technique which we encountered in section 5.1. Then we convert the labels and predictions via label encode to integer arrays, label test, and predictions test. We can now calculate the correlation coefficient between the predictions and the known labels of our test data, which indicates whether there is a statistical linear relationship or dependence between the actual and predicted values. This comes out quite high indeed. The R-squared value, or the coefficient of determination, is a number that indicates how well data fits into a statistical model. It also results in a high value here. If we visually compare predictions and actual data, we see that only one prediction is wrong out of 37. Drawing a scatter plot of predictions versus actual data using Winston, we obtain the following graphic. One false prediction is responsible for the outlier. We can calculate the receiver operating characteristics, or ROC characteristics, of our model. From this, we can see that it performs very well. We can also apply an n-fold cross-validation scheme. You can see the complete results in the code file. The resulting mean accuracy gives us the most relevant information. If we do this for a range of purities, we get an even more accurate result. A visualization of these results, here with Gadfly, helps to clarify them. It is clear that the model has achieved a very clear classification. In this video, we have applied a decision tree model in a more realistic way by training the model and then testing its prediction accuracy. We used correlation and ROC characteristics to see how good the model performs. In the next video, we'll apply a generalized linear model to our dataset to obtain a regression model relation between the features and the target. In the previous video, we looked at training and testing a decision tree model. In this video, we're going to take a look at regression techniques, more specifically using a generalized linear model. Regression methods are supervised learning models that deliver a numerical relationship between the independent variables, the features, and the dependent variables, the labels or targets. They also give us a measure of how strong this relationship is. The package multivariate stats contains various methods for doing linear regression, ridge regression, and principal component analysis. Here, we'll be looking at two other packages for regression analysis in Julia, GLM and GLMNet. Let's get both of those loaded so we can begin. Many of the specialized regression methods fall into a class of generalized linear models, GLM. Using a GLM, linear models can be generalized into other patterns via the use of a link function, which specifies more complex forms for the relationship between x and y. This allows regression to be applied to almost any type of data. In the case for more than one independent variable, x becomes a matrix, often denoted as x with a capital letter. Let us first revisit the relationship between sepal length and sepal width, discussed in section 4.3. As usual, We read in our iris dataset, and we prepare a data frame data with two columns X and Y, containing the data in which we are interested. A simple linear model can be obtained through the LM function, as shown here. LM takes the data frame data as second parameter and a formula y tilde x as first parameter. A formula is a representation of a linear model type expression of the dependent variable y as a function of the independent variables x. The calculated model closely approximated our earlier lin-reg solution, but the model also provides standard errors and PR or p-values. A p-value lower than 0.05 shows a statistically significant relationship between x and y, which is clearly the case here. LM is a shortcut for fit linear model formula data. Here we see the format for a generalized linear model. The family specifies a distribution, and the link function specifies more complex forms for the relationship between x and y. We use normal distribution, so we assume the values are symmetrically distributed around a center value. The fourth parameter is an identity link function, which means we are applying a simple linear regression where we expect the residuals to have a normal distribution. In the data frame data, any rows containing NA values are ignored. The result is the GLM model shown, providing an identical solution to our LM model earlier. Separate functions exist to interrogate the model for its details, for example, coef for the estimates of the coefficients, stdir for the standard errors of the coefficients, vcov for the variance-covariance of the coefficients, estimates, in other words, the associated covariance matrix, and deviance for the RSS, the residual sum of squares, of the model, which is a measure of the model fit. The sepal length values that the model predicts are given by the predict method. Let us plot this method with Gadfly. Obtaining the following plot, where x represents the sepal width and y the sepal length. The GLM net package, which closely resembles the R package with the same name, fits entire lasso or elastic net regularization paths for linear, logistic, multinomial, and Cox models using cyclic coordinate descent. It uses the Fortran code for GLM net. The lasso package is a pure Julia implementation of the GLM net coordinate descent algorithm that often achieves better performance. Let's investigate the relation between sepal width combined with petal length and sepal length as the dependent variable. Running GLM net will fit models of various values of the regularization parameter lambda. The result is a set of 58 different models. We'll have a look at the intercepts and coefficients of the first 10 models, which correspond to the largest values of lambda, given by path A0, 1:10. Coefficients are held in the betas field, which is an array with a column for each model and a row for each coefficient. Since the first few models are strongly penalized, each has only a few non-zero coefficients. Now we have models for a variety of lambda. How do we know which one is best? Apply cross-validation with GLM net CV. In this video, we have learned how to use generalized linear models on data from Julia. In the next video, we'll explore the use of support vector machines in data science. Hi, and welcome to section 5.5, entitled Working with Support Vector Machines, or SVM for short. In the previous video, we looked at generalized linear models. In this video, we're going to take a look at how support vector machines are used in modeling. and we'll show how optimizing the training dataset can improve accuracy of the model. SVMs are supervised black box model machine learning algorithms that can be adapted for use with nearly any type of learning task, including both classification and numeric prediction. They are especially effective in working with image data for pattern recognition. They are capable of learning and recognizing complex visual patterns with a high degree of accuracy and without being overly sensitive to noise. The SVM algorithm builds a binary classification model based on a training dataset and assigns new examples into one category or the other. The Lib-SVM library is a widely used open-source support vector machine program written in C++. Julia has a package with the same name that has bindings for this library. Let's apply this to our iris dataset. We'll train our SVM model on a part of the length and width features combined with its species name. Then we'll test our model and predict the species name for the remaining feature measurements, comparing the predicted species with the actual species. So, the model will try to divide the data into 3 species classes, based on the 4 feature measurements. For the training data, we'll take the rows with odd index, and for the test data, the rows with even index, as shown on the screen. Each of these arrays has length 75. Now we can train our SVM model with the SVM train method, using the training labels as first argument and the training features as second argument. Note that the features matrix in the second argument needs to be transposed with the tick operator. The SVM predict method takes the model as its first argument and then transposed test feature matrix as its second argument. It returns a tuple with the predicted labels as first element. By comparing these with the test labels, we obtain a measure of the model's accuracy, which is 93%. Not that bad. Predicted underscore labels dot double equals labels underscore test gives us a 75 element array with true, false values. True if the prediction was correct, and false otherwise. Mean converts these into ones and zeros. If they are all true or 1, we would have 100% accuracy. Using the decision tree package, which we covered in sections 5.2 and 5.3, we can calculate the confusion matrix as shown here. Remember from section 5.1 that the confusion matrix is an evaluation of the performance of a classification model based on the counts of test records correctly and incorrectly predicted by the model. The rows are the actual class, and the columns the predicted class. In our case, we see that all 25 setosa specimens were predicted correctly. From the versicolor, 1 was incorrectly classified as virginica, and from the virginica, 4 out of 25 were incorrectly classified as versicolor. 93% accuracy is not that bad, but this was obtained with 50%, 75 records, of the data used for training. Moreover, the data were not obtained in a random way. Now, we'll use 80% of the records for training and 20% of the records for testing. Applying a best practice, we choose them in a random fashion, with the shuffle method, like shown on the screen. Now, we filter our labels and features arrays with the train rows to obtain the training and testing data. Applying the same procedure as detailed higher, we can now obtain a precision of nearly 97%, which is extremely good. All setosa and versicolor are predicted correctly, and only one virginica specimen was predicted as a versicolor specimen. In this section, we have learnt to apply some more advanced machine learning techniques to data. Classification with decision tree, linear regression with GLM, modeling with SVM. We have now come to the end of this course, of which we invoke the main themes on the screen. We retrieved our iris data from files and databases, and learned how to use statistical calculations and visualization techniques on these data. Also, we applied decision trees, generalized linear models, and support vector machine modeling to these data to discover different relationships. The story does not end here. Julia is also applied in artificial intelligence techniques such as neural networks and deep learning. The most promising packages in this field are Mocha, MXNet, and Strada. Throughout the numerous examples that we have seen, that the Julia language and ecosystem is indeed suited for use in data science projects, and is indeed a viable alternative for the more mainstream choices like R and Python. Armed with this knowledge and skills, I encourage you to apply these to the data of your past and future projects. If you need help, ask for guidance on the mailing lists of Julia statistics, or on the general Julia mailing list. Julia will grow more and more mature to its 1.0 version, and in particular for Julia statistics, we can expect even better DataFrame support, GLM modeling, and automatic generation of Markov chain Monte Carlo, MCMC, code for Bayesian models. Keep an eye on the Julia Stats website for new and improved functionalities in the data science field. I hope you've enjoyed watching this series and experimenting with Julia code on data, and wish you much success with it in projects to come.